Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. Lagrange Points. The celestial sweet spots. Lagrange points are fascinating regions in space where the gravitational forces of two large bodies, such as the Earth and the Moon, or the Sun and the Earth, create areas where a smaller object can maintain a stable position relative to the two larger bodies. Named after the Italian-French mathematician Joseph Louis Lagrange, who first described these points in 1772, Lagrange points have become crucial in modern space exploration and research. There are 5 Lagrange points in any two-body system, labeled L1 through L5, each offering unique opportunities and challenges for scientific study and space missions. The concept of Lagrange points arises from the three-body problem in celestial mechanics, which explores the gravitational interactions between three masses. While the general three-body problem has no exact solution, certain configurations allow for stable points where the gravitational forces and the centrifugal force balance out. These points, where a small object can remain stationary relative to the two larger bodies, are the Lagrange points. L1, L2, and L3 are known as collinear Lagrange points because they lie along the line connecting the centers of the two large bodies. L1 is located between the two bodies, where the gravitational pull of the larger body partially cancels out the pull of the smaller body, creating a point of equilibrium. L2 lies beyond the smaller body, on the opposite side of it from the larger body. At L2, the gravitational forces combine with the centrifugal force to create a stable point. L3 is on the opposite side of the larger body from the smaller body, effectively forming a straight line with the two bodies. L4 and L5, often referred to as the Trojan points, form the apexes of two equilateral triangles with the two large bodies. These points are located 60 degrees ahead of L4 or 60 degrees behind L5, the smaller body in its orbit around the larger body. Unlike L1, L2, and L3, which are points of unstable equilibrium, L4 and L5 are points of stable equilibrium. This means that objects at these points can remain there with little to no corrective effort, making them particularly interesting for long-term space missions and potential colonization. The Lagrange points have been utilized in various space missions, leveraging their unique gravitational properties to facilitate scientific research, communication, and observation. One of the most well-known examples is the use of the L1 point for solar observation missions. The Solar and Heliospheric Observatory, SOHO, a joint mission by NASA and ESA, has been stationed at the L1 point since its launch in 1995. From this vantage point, SOHO can continuously monitor the Sun without the interference of the Earth's shadow, providing invaluable data on solar activity and space weather. Similarly, the L2 point has become a popular location for space telescopes and observatories. The James Webb Space Telescope is stationed at the L2 point, where it can maintain a stable position with minimal fuel consumption. The location offers a clear and unobstructed view of deep space, making it ideal for observing distant galaxies, stars, and other celestial phenomena. Additionally, the L2 point's stable thermal environment helps to maintain the telescope's instruments at the necessary low temperatures for infrared observations. The L3 point, while less commonly used, holds theoretical interest for scientists studying the dynamics of the Earth-Sun system. Positioned on the far side of the Sun, directly opposite the Earth, L3 is perpetually hidden from our view. Although it is an unstable point and not suitable for long-term missions, it has been proposed as a potential location for a solar observation platform that could provide early warnings of solar storms and other space weather events that might impact Earth. L4 and L5, with their stable equilibrium, present unique opportunities for space exploration and potential colonization. These points are often home to a group of small asteroids known as Trojans, which share the orbit of a larger planet. The most famous examples are the Trojan asteroids of Jupiter, which populate the L4 and L5 points of the Jupiter-Sun system. Similar Trojan asteroids have been discovered in the Lagrange points of other planets, including Mars and Neptune. The stability of L4 and L5 makes them attractive targets for future space missions. These points could serve as staging areas for missions to the outer planets or as locations for space habitats and research stations. The presence of Trojan asteroids also offers opportunities for resource extraction, providing raw materials for construction and fuel for space travel. Some scientists have even proposed the idea of using L4 and L5 as waypoints for interstellar travel, taking advantage of their stable orbits to facilitate the assembly and launching of spacecraft bound for other star systems. The use of Lagrange points is not limited to scientific research and exploration. They also play a crucial role in communication and satellite technology. For example, communication satellites positioned at L1 can provide uninterrupted coverage of the Earth-Sun system, relaying data between the Earth and solar observation missions. Similarly, satellites at L2 can maintain a stable position for deep space communication, ensuring a reliable link between Earth and distant space probes. The concept of Lagrange points extends beyond the Earth-Sun and Earth-Moon systems to other two-body systems in the solar system. Each planet and its moons, or the Sun and a planet, create their own set of Lagrange points, each with unique characteristics and potential applications. For instance, the Lagrange points of the Sun-Earth system differ from those of the Sun-Jupiter system due to the vastly different masses and distances involved. As our understanding of celestial mechanics and gravitational interactions advances, the potential applications of Lagrange points continue to expand. Future missions may take advantage of these points for interplanetary travel, using them as waypoints or refueling stations. The stable environments of L4 and L5 could support long-term habitats or research outposts, advancing our capabilities in space exploration and utilization. One of the most ambitious proposals involving Lagrange points is the construction of a space elevator. A space elevator would consist of a tether extending from the Earth's surface to a satellite in geostationary orbit. The L1 or L2 points could serve as anchor points for such a structure, providing the necessary stability and minimizing the forces acting on the tether. While the engineering challenges of building a space elevator are immense, the potential benefits in terms of cost-effective space travel and transportation are equally significant. In addition to their practical applications, Lagrange points offer a unique perspective on the fundamental principles of gravity and motion. They serve as natural laboratories for studying the dynamics of multi-body systems and the interactions between gravitational forces. By exploring and understanding these points, scientists can gain deeper insights into the behavior of celestial objects and the fundamental forces that govern the universe. The study of Lagrange points also has implications for the search for extraterrestrial life. The stable environments of L4 and L5 could potentially support microbial life or other forms of life that thrive in low-gravity conditions. The presence of water and organic molecules on some Trojan asteroids further enhances the possibility of finding life in these regions. Missions to explore the Lagrange points and their associated asteroids could yield valuable information about the potential for life beyond Earth. In the broader context of space exploration, Lagrange points represent a key milestone in our journey to understand and utilize the cosmos. From their discovery by Joseph Louis Lagrange in the 18th century to their modern applications in space missions and research, these points have continually expanded our knowledge and capabilities. As we venture further into space, the Lagrange points will remain essential waypoints, guiding our exploration and shaping our understanding of the universe. The future of space exploration will likely see increased utilization of Lagrange points for a variety of purposes. Advances in propulsion technology, robotics, and materials science will enable more ambitious missions to these points and beyond. As we continue to push the boundaries of what is possible, Lagrange points will remain a central focus of our efforts, offering new horizons and challenges in the quest to explore and understand the cosmos.